Okay, now just continuing with exercise 7E, just looking at another question. If we look at where we finished, this was question 4. So we were solving these inequalities. Now, these we didn't need to take logs of both sides or anything like that, because you can write 1 as a power of 4. So 1 is 4 to the 0. Also in this question, 64 can be written as a power of 2, so 2 to the power of 6. So these were able to be solved. And this one as well. In question 4, H, 0.01 could be written as 1 over 10 squared, or 10 to the power of -2. So these were able to be, we were able to solve those. Now, in question 6, however, if you're trying to solve something like, so question 6F, solve 3 to the power of x is less than or equal to 0.007, you cannot write 0.007 as a number with base 3. So with this type of question, you need to take logs of both sides. So just as we were taking logs of both sides with equations with equal signs, you can do the same with inequalities, as long as this number here, this if it's of the form a to the power of x, as long as the a is greater than 1. So we're just going to take logs of both sides. I'm going to take ln of both sides. And now the x comes to the front. Now we're dividing by ln3. Now we know that ln3 is positive. So we're dividing by a positive number, so the inequality sign does not need to change. However, if we were dividing by ln of 0.007, ln of a number between 0 and 1 is negative. You would have to change the inequality sign around, but we're not dividing by a negative quantity. We're dividing by a positive number. So x is less than the log of 0.007 over ln3. So remember, this numerator will be negative because it's the log of a number between 0 and 1 divided by log 3, which is positive. So we're getting a negative answer. So that is the solution to our inequality, and they want it to 3 significant figures, so it would be negative 4.52. Okay, to 3 significant figures. Okay, just another question there as well. I'll just do it over here. Question 6G, just the same again. 1.2 to the power of x is greater than 10. Okay, look, you can just take ln of both sides, or you could take log to the base 10 of both sides. I'm just going to do log to the base 10 of both sides for this one, because I've got the number 10 there. But you could just take ln of both sides. I just want to do this here, just to show that you could do it as well. So remember, this x comes to the front, so it's x times log to the base 10 of 1.2 is greater than, now log to the base 10 of 10 is 1. So x is greater than log to the base 10, x is greater than 1 divided by log to the base 10 of 1.2. Now on your calculator, that is just the log button. Okay, so we just go... now log of 1.2, that's positive. So if you just do that on your calculator, log of 1.2, you can see that it's a positive answer, so it's fine. So 1 divided by log of 1.2 is, you'll get x is greater than 12.6. They want it to 9, etc., and they want it to 3 significant figures, which is 12.6 to 3 significant figures. Okay, now with this question here, I could have also just taken ln of both sides as well. So if you want to try that, you can, but you should get the same answer. Okay, the only reason I did, so you can do ln of both sides like over here, or log to the base 10 of both sides. I just did log to the base 10 here because log to the base 10 of 10 is 1. Question 5, just looking at question 5. So an inequality with a log. So we know that 5, remember 5 is the base. So we're trying to work out what x is. So x will be greater than 5 to the power of 0. So x is greater than 1. Now that is one way to do this question. The reason we're able to do this is that as long as, if we've got something in the form of log to the base a of x, as long as the a is greater than 1, then the inequality sign does not need changing. So we're trying to work out what x is, okay? So x is 5. 5 will always be the base, 5 to the power of 0. So x in this case is greater than 1. Okay, so you could try that out. You could try if x is 2 and work out what that is, and you should get something greater than 0. So log to the base 5 of 2, to work that out, it would be, say, ln 5 divided by ln 2. Okay? And when I get ln 5 divided by ln 2, I get a number greater than 1. I get 2.32. Okay, now another way you could do this is as follows. Now, we saw earlier last lesson the rule that log to the base a of a is 1, but a to the log of base a, sorry, yeah, that's right, a to the power of log base a to the x happens to be x. I'll write this one out as well. So we also know that log to the base a of a to the power of x is also x. So we looked at these two rules last lesson. So if I look at this first rule here, a to the power of log to the base a of x is x, I could take, in previous questions we were taking logs of both sides. I can take both sides to the power of 5. So I can put both sides to the power of 5. I can do that. So not taking logs of both sides because I've already got logs there. And the sort of inverse of logs is your index. So raising both sides to the power of 5. So what I'm here doing is raising both sides to the power of 5. Now that uses this rule here, a to the power of log base a of x equals x. So that means the 5 log to the base 5 goes, and I'm just left with x is greater than 5 to the power of 0. In other words, x is greater than 1 as before. Okay, just an alternative way of doing that. Another example there is solving. This is just an example. Log to the base 10 of x is greater than or equal to 4. Okay, so I could do that a few different ways. I can write x as an index, so x is greater than or equal to, now remember 10 is the base, so it's the base over here. 10 is greater than or equal to 10 to the power of 4, or greater than or equal to 10,000, or, actually I'll do it over here, or I could start with log to the base 10 of x is greater than or equal to 4 and raise both sides to the power of 10. So 10 to the power of log to the base 10 of x is greater than or equal to 10 to the power of 4. 10, this is of that format, a to the power of log base of a to the x, that just equals x is greater than or equal to 10 to the power of 4, which is the same answer as there before. X is greater than or equal to 10,000. Now for another question from question 5 here, just working this one out, evaluating this, or solving for x, sorry. So solve for x again. We can do just writing what x is here. Remember, log to the base 6 of x is less than 1. So x will be less than, 6 is the base, so 6 is the base over here. X is less than 6 to the power of 1, so x is less than 6. Or you could start with log to the base 6 of x is less than 1 and raise both sides to the power of 6. So raise both sides to the power of 6. So we go 6 to the power of log base 6 of x is less than 6 to the power of 1. They cancel. X is less than 6. Okay, so just showing you two ways of doing those questions. The questions here, some are equations, some are inequalities. So looking at question 10, A and C. Now, before you go taking logs or anything like that, just see whether, I've got here base 2, if 16 can be written as base 2, that would be the easiest way to answer this question. So 2 to the power of x plus 1 equals 16, but we know that 16 is 2 to the power of 4. So because the bases are the same, I can just equate the indices. So x plus 1 is 4. In other words, x is 3. Now we can also do the same here. I've got 2 to the power of x minus 1 is less than 1, but I can write 1 as a base 2 number, and that would be 2 to the power of 0. So therefore now, because the bases are the same, I can just compare the powers. So therefore x minus 1 has to be less than 0, so x has to be less than 1. So what we can do, let's just substitute a number less than 1, such as 0. Let's just check our solution. Let's sub x is 0 into the original equation. You would get 2 to the 0 minus 1, 2 to the negative 1. Well, that's a half, because it's 1 over 2 to the power of 1, and that does happen to be less than 1, so that does look correct. Okay, now for question 10e. So we've got a half to the power of x minus 3 equals 8. Well, I could write 8 as 2 to the power of 3. So I can also write this half as 2 to the power of something. So a half is really 2 to the power of negative 1. So the reason we're doing this is that this side, the right-hand side, has got 2 as a base. I'd like to make the left-hand side as base 2 as well, and 1/2 is 2 to the power of negative 1, so I need to expand my brackets here. So I get 2 to the power of negative x, and negative 1 times negative 3 is positive 3, equals 2 to the power of 3. So now I can equate my indexes, so therefore negative x, or my indices, negative x plus 3 is 3, and so therefore x must equal 0. So let's just check. So a half to the power of 0 minus 3 is a half to the power of negative 3, which is 2 cubed, okay, which is 8. Okay, so that looks correct. Looking at this question over here, 1/10 to the power of 5x equals 1/10. Well, this one we're fairly lucky, because 1/10 is just 1/10 to the power of 1. So we've got the same bases here, so we're just equating the indices that 5x would equal 1. Therefore, x is 1/5. Now, just another question. Looking at question 9 in your exercise, just a couple of those. So we're going to use the log laws to prove the following. So use the log laws to prove that log to the base of 1 on a of x equals negative log to the base a of x. Now this one's a little bit tricky. Okay, so let's start with our left-hand side. Our left-hand side is log to the base 1 on a of x. Now, the only thing you can really do here is use the change of base rule. So I'm going to do change of base with log to the base 10. So log to the base 1 on a of x is log to the base 10 of my number over log to the base 10 of my base down there. Now, I've got log to the base 10 of x over, now log to the base 10 of 1 on a is log to the base 10 of a to the power of negative 1. Because 1 on a, 1 over, is a negative power, it means the power of negative 1. Now I'd like to move this, keep the numerator the same, so it's log to the base 10 of x over. Now log to the base 10 of a to the negative 1, the negative 1 can come to the front, so it's negative log to the base 10 of a. So now a positive divided by a negative is a negative. And now I'm just going to use the change of base rule in reverse, so that's just log to the base a of x. So the negative, positive divided by a negative is a negative, and log to the base 10 of x over log to the base 10 of a is really just using the log change of base rule in reverse. Now the change of base rule is the following. For example, if I want to write log to the base a of x as log to the base 10, I go log to the base 10 over log to the base 10 of x over log to the base 10 of a, using my change of base. So I'm just doing this, I've got this, doing it in reverse. So that equals what we're trying to prove, which is negative log to the base a of x. Right, and just another one of those. Question C in the exercise. So we're trying to prove that log to the base 1 on a of x to the negative 1 equals log to the base a of x. Let's start with our left-hand side, which is equal to log to the base 1 on a of x to the negative 1. So we know we can put this negative 1 out the front straight away. So that's negative log to the base 1 on a of x. And this bit is pretty much what we had before. So that will be just the negative of log. Now I'm going to do this to log to the base 10, do a change of base. So it's negative log to the base 10 of x over log to the base 10 of 1 on a. Now I need to change the way this 1 on a looks. So it's negative log to the base 10 of x over log to the base 10 of a to the power of negative 1, because 1 on a is a to the negative 1. So notice we're writing out each step. If you're asked to prove something, you have to show each step. You can't just jump a few steps. Now log to the base 10 of a to the power of negative 1, the negative power comes to the front. So that's negative log to the base 10 of a. And now I will just use my change of base again. A negative divided by a negative is a positive. And I've got log to the base 10 of x over log to the base 10 of a, which I'm using this and going in reverse, which is log to the base a of x, which equals the right-hand side. Okay, so that's that second one. 23. This is the example in exercise 6e before the exercise. Now it says the rabbit population on Cannon Island is doubling every year. So for example, you might start with 2 and then 4 and then 8 and then 16, etc. That's just showing how the number 2 doubles, for example. You know, this could be 2 to the 1, that's 2 squared, 2 cubed, 2 to the power of 4, 2 to the power of 5, etc. That's just showing the number 2, for example, doubling. But, you know, it may not be that we did start with 2 rabbits on the island, okay? So a few years ago, a study estimated that there were 500 rabbits there. So let's say there were 500 rabbits there and it was doubling every year. It would be 500, and then 500 times 2, which is, say, 1,000. Actually, I'll write it like this. So let's say there were 500 and then 1,000, and then that doubles 2,000, and then that doubles 4,000, etc. But I want to write that in terms of powers like this. So I would have 500, 500 times 2. This would be 500 times 2 times 4, really, which is 2 squared. So this would be 500 times 2 to the power of 1, 500 times 2 squared. This one would be 500 times 8, or 500 times 2 cubed, and so on. So my general expression for the population would be 500 times 2 to the power of n, where n is the number of years. Okay, so the population, I have created a formula for that, and it's 500 times 2 to the power of n. Now this is just an exponential function. However, you do have a constant term here at the front, and this 500 has got nothing to do with this power of n here. Okay, so we've just shown that, for example, if there were 500 and then 1,000 and that doubles to 2,000, we need to come up with one formula that is able to, that you can substitute a value of n to show all these values. Now some of you might be thinking, well, how does this formula fit in with the 500? Well, 500 really is 500 times 2 to the power of 0, because we know that 2 to the power of 0 is 1. So that means that the initial population, so for example here, when n is 0, my population is 500 times 2 to the 0, which is 500 times 1, which is 500. You know, when n is 1, like after 1 year, the population is 500 times 2 to the power of 1, which is 1,000, and so on. Okay, so that is our formula for the population. Okay, and then the question is, how many years later will the rabbit population be 10,000? So we're going to substitute p is 10,000 and solve. And solve or find n. So we've got that 10,000 equals 500 times 2 to the power of n. So 10,000 divided by 500 is 2 to the power of n. So you've got 100 over 5, so that's 20 equals 2 to the power of n. So now we're not going to be guessing anymore. We don't guess. We can just take logs of both sides. You could take ln of both sides if you want. So ln of 20 equals ln of 2 to the power of n. So ln of 20 is, remember bringing the n to the front, is n ln 2. And now to find n, we divide by ln 2. So don't try anything fancy here, you just need to enter these on your calculator. There is no log law for ln 20 divided by ln 2. So divided by ln 2, and we get 4.32. The answer to the nearest tenth of a year. If I substitute n is 4.3, I will get less than 10,000. Let's try. So if I check, if I sub n is 4.3 into my population equation, it is not going to be, the population will not have hit 10,000 yet. So trying that, 500 times 2 to the power of 4.3 should give me a little bit under 10,000 rabbits, so it's not 4.3. So this here is my answer in exact form. So this is my exact form for my number of years. And then to the nearest, you're going to need more than 4.3 years because they want it to the nearest tenth of a year. You won't have achieved 10,000 rabbits yet. So if I substitute in the n is 4.4, I get 10,556. Okay, so you need at least 4.4 years, but look, I suppose it is closer to 4.3 years than 4.4 years anyway. Just one extra little thing on exercise 7D. There were just some harder questions at the end. Just remembering these rules. That log to the base a of a to the power of x is x, and a to the power of log to the base a of x equals x for all real x greater than 0, and where a is greater than 0 and a not equal to 1. All right, so these laws apply when a is greater than 0 and not equal to 1. So just some examples here. To simplify the following, log to the base 7 of 7 to the power of 12. Well, we know with this one, you would bring the 12 to the front anyway. So you've got 12 times log to the base 7 of 7. And log to the base 7 of 7 is 1, so that just equals 12. Okay, so that's just using this rule up here. But you actually don't really need that rule because you can know to put the power of 12 to the front. Okay, and another one there, to simplify 5 to the power of log to the base 5 of 11. Now this is when we look at this second rule here. So a to the power of log to the base a of x equals x. And we did look at this in one of our earlier questions. 5 to the power of log 5, well, that all just goes and you're just left with 11. Now, in some questions, you might be asked to write, for example, 3 as a power of 10. Now, the way we do that, we use this second law here, okay? So write 3 to the power of 10 using the fact that a to the power of log to the base a of a, log to the base a of x equals x. So we need to write 3 as a power of 10. So 10 needs to be my base. So I would use 10 to the power of log to the base 10 of 3. We know that they all cancel, equals 3. So this way I'm writing 3 as a power of 10. Okay, and another example is to write 7 as a power of 2. Okay, using that same rule. So I'd have to have 2 as my base. So 2 to the power of log to the base 2 of 7 equals 7. So therefore 7 is written as a power of 2, 2 to the power of something. Okay.